So my name is Yongyun Hu, and my collaborators Jun Yang and Darren Abbot from University of Chicago, and Yungang Liu from Princeton University. Okay, this is just for fun, because the last day of EGU, usually not many people, and we also got bored. So nobody really knows what the great thinker is thinking about. Here, I would assume he's thinking about, are we alone in the universe, or are they there? Well, we are thinking about the audience also thinking about us. Okay, by December 9th, 2014, 1,854 exoplanets have been discovered. People would think like 20 of them are potentially habitable. If we look at this, Earth is here, this is Mars, Jupiter, and Neptune. If we look at those 20 exoplanets, most of them are still larger than Earth. We usually call that super Earth. We should see, so far we don't really find anyone really like Earth. We are most interested in habitable planets around M stars, because M stars has the highest population in the universe, and also it's easier to detect habitable planets around the M stars. However, because the habitable planets, the habitable zone is so close to the M star, usually if we find planets in the habitable zone, usually the planet should be tidal-locking. For tidal-locking planets, people are worrying about like three kind of problems. One is the uneven heating, like this one. This side is the day side, this night side. So if the night side temperature is too low, first atmosphere could be collapsed on the night side if the temperature like this. This is the freezing point of CO2. Or if water is completely trapped on the night side, if the temperature less than 0 degrees C. Another problem is people worry about, usually people would think, or the theories predicts M stars have very strong extreme ultraviolet radiation, can that hurt the atmosphere or even life? So, but today I would focus on this one. So in 2013, Christian Mano published a paper. He proposed the three configurations of the, he assumed that's Arca planet. The three configurations of water or ice. The first one is the ice shelf. The second one is the ice sheet. The third one is the water completely trapped on the net side. So here we look down. This is the pole. Here is the sub-stellar point, anti-stellar point. So for the first configuration, so you would have like a thin or thick ice, sea ice on the net side. For the second one, the water is completely frozen on the net side, but you still have liquid water on the day side. So for this one, so water completely frozen on the net side. You would not have much water on the day side. So here, this is less water for this direction, and this also temperature too low. So that means, particularly, we would think if this would happen. If this happens, you don't have liquid water on the day side, so the planet should be uninhabitable. In 2004, I think January, we published a paper. We ran the coupled atmosphere ocean GCM. We show that the CS is actually very thin for Arca planet. The CS thickness I think no more than 6 meters on the night side. I think this area, the two subpolar areas. Here, this is the open ocean area. This is the sea ice, the white region. The sea ice thickness we can see here. It's no more than 6 meters. If we increase the CO2, this open ocean area larger. The maximum sea ice thickness also about like 5 or 6 meters. That means if you have arc planet, you don't have to worry about that very much because ocean heat transport can warm the night side very well, and sea ice not very thick. Not very. Okay, for this talk we want to test for that ocean we have the ocean depth is 4 kilometer deep. We wanted to test for shallow ocean, or if the planet has a continent. We still use a modified Earth climate model. We use this typical planetary parameter for habitable planets. And we also use the glacier model from University of Toronto. We set experiments, numerical experiments with this shallow ocean. And we also consider supercontinent on the day side. We even tried the continent with the Earth, the modern Earth continent configuration. So basically, we wanted to ask the two questions. Does ocean depth influence sea ice thickness? And what about land glacier thickness? So those two are the two shallow ocean experiments. This is like the ocean depth only like 325 meters. This is 815 meters, much shallower than the 4 kilometer ocean. We can see here, this is the sea ice thickness. This is the open ocean area, the blue area. And here you can see the maximum ocean sea ice thickness. It's only about also about 6 meters, no more than that. For this one, the ocean is slightly deeper. We also see the maximum ice thickness here. Also no more than, it's about around 5 meters. This is the temperature, surface temperature we see corresponding to the open ocean area. You can see the warm temperature here and the colder temperature around the minus 60 degrees C. The arrows those arrows show the sea ice movement. Those arrows show the surface wind. Here, so in this plot, we show the heat. This is the heat flux. It's not the horizontal heat flux. It's the heat flux between from ocean to ice. So here, that means this area, a lot of heat from ocean to ice or mild ice. This is the vertical temperature, ocean temperature. I should say the potential temperature. This is for the shallow one, a slightly deeper one. We should say the two had no very significant difference. Of course, this deeper ocean would have stronger or more heat transport. So this plot gives the different factors which determine the sea ice thickness. We can see this one. This is the thermal dynamic factor. This is the dynamics. The thermal means the temperature. If the surface temperature or ocean water temperature are high, which can melt sea ice. If that's low, sea ice can form. So this means the sea ice dynamics basically means the wind, atmospheric wind can transport the sea ice from the night side to the day side. So we can see basically the two cancels out each other. At the night side, the thermodynamic factor causes sea ice formation, but the dynamics, the wind blows the ice from to limit the ice growing. So those are very detailed things, so I would not to say very much here. So that's for the shallow ocean. If we consider supercontinent on the night side, we assume supercontinent on the night side. So here is the anti-star point. This is the day side. This is night side. So this plot shows the surface temperature, the lowest temperature here and here, the subpolar regions. This is the precipitation, the strongest precipitation also in the subpolar regions. Basically, simply speaking, the land glacier thickness is determined by 3 key factors. One is the surface temperature, the other one is the precipitation, and also very important one is geothermal heat flux. This one is quite small. For the modern Earth climate research, we usually just neglect that. But for the glacier study, it's very important. It's very important to determine how deep the land glacier thickness could be. We can look at this one, this color bar. For this 0.1 watt per square meter, so how we get the results? We first run the coupled atmosphere ocean model, then we use that model output to input to the glacier model to get this result. The maximum land glacier thickness is about 2 kilometers. So in this area, maybe it's only 1 kilometer in depth. So the arrows shows the glacier motion. We can see that. So this on the night side. The land glacier thickness is no more than 2 kilometers. That means if you still have like a 4 kilometer deep ocean, consider the water freezing here, condensation here on the night side, your day side still have like a 2 kilometer ocean in depth. So that means you would not have water completely trapped on the night side. So here we try the different geothermal heat flux because it's the most important factor to determine land glacier thickness. What I showed is this one. Then if you decrease the geothermal heat flux, then the glacier thickness can be like 3.5 kilometers. If you reduce that geothermal by 1 order, this can be like 6 or 7 kilometers. So we use the modern Earth continent configuration. We can see here, this plot shows the sea ice. We can see the Pacific is okay. This is a substellar point. So the Pacific is almost ice-free because temperature above 0 degrees C. The Atlantic, particularly North Atlantic, the sea ice can be like 100 meters. It's not that deep, that thick. Very interesting thing we see here, the Bering passage or the Drake passage. If you have the very small passage, you still have heat transport, and you have sea ice transport. So the southern Atlantic Ocean, the sea is very thin. And even the Arctic Ocean, the sea is very thin. Only in the something like the lakes or the close ocean areas, the sea ice can grow to like 100 meters. This plot shows the land glacier. We can see the Antarctic land glacier is close, like 3 kilometers, roughly equivalent to today's Antarctic land glacier thickness. It's fortunate we still can see the San Francisco area should be glacier-free, so we still can have HU here. We don't have to worry about that. I should have passed. Skip this one. Okay, finally we propose like our three configurations. This one. If the planet is a water planet or arc planet, the sea ice should be thin on the net side. We do not have to worry about water trapping. So for this one, if we have supercontinent on the net side, but the geothermal is strong or close to the Earth, today's geothermal heat flux, Usually the ice glacier thickness not very thick. We also don't have to worry about water trapping. Only for this case, the geothermal is very weak and the ocean not very deep. Then for this case, the water could be completely trapped there. So I just skip the conclusion to give this one. So according to the movie, a water planet was discovered. Okay, thank you.
Very quick questions? There's a lot of information in this talk. Yes.
Did you consider any situations with the continent on the dayside? Because I think that the way the gravitational potential energy works, it would tend to orient itself if it was tidally locked with the continent on the dayside, but I'm not sure about that.
Yes, I have this one here. If you consider the continent on the dayside, the night-side ocean would be completely frozen eventually.
Okay.
But if we consider the tectonics, the continent can drift, so that's just a short period or something like that.
Great, thanks.
Thank you.